Morning.
Good morning, sir.
So I would like to just take some feedback about the course. How are you feeling about this course? Are you at ease with the course, or are you finding any difficulties in following, especially when you are learning online? This particular course is more of a practice course. You need to practice with your own hands. You have to solve problems with your own hands, and then things will be much clearer. So, are you all right, or should I go? Should I be a little bit slower or teach in a different way? How about the theory part? How about the numericals? Can anybody give some feedback?
Sir, the speed, I think if it's reduced a little bit, it will be better. Just a
Okay.
little
Is,
bit.
is it theory or the numericals?
Numerical.
Numericals. Huh? Okay. I'll see. I'll try that today. So today and next class also we'll continue with the numericals. Usually I come assuming that I can solve about 3 numerical problems in a class. So maybe I can try to decrease that. We'll see, depending on the length of the problem. Some of the problems in heat transfer, especially in convective heat transfer and radiative heat transfer, they can be extremely long. In fact, in radiation, we have some problems which can take about 40 minutes to solve for the first time. But if you are experienced, you may be able to finish it in 20 minutes, 20-25 minutes. But that is how the problem, nature of the problems are in heat transfer. You will have to, what happens in this course is that you will have to refer to the data book quite often to read or to pull out the property values, the correlations, the equations, and so on. So that is something which consumes some time. Okay, and as I said, you should also be familiar. You should make yourself familiar with the data book so that you don't lose time in searching for information. So that is something that I want you to know. Okay, so in today's class, I will take up a few more numerical problems. And in the next class also, on Monday's class also, I will continue with numericals. And since I think we have some time, enough time before CAT 1, therefore I would like to spend one class on introducing you to a software called Interactive Heat Transfer. The name of the software is Interactive Heat Transfer. It is available freely online, so you can download it. I will give you the link to download. You can install it in your computers, and you can solve some problems. I won't say you will be able to solve every problem in heat transfer, but you will be able to solve a good number of problems, especially open-ended problems, design kind of a problems. That software has got some capabilities. So I will introduce you to that software, and you can find out what can be done using that software. Okay, so that will be the agenda for the next 3 classes, including today's class. So today, Monday and Tuesday, this is what we will be doing. All right. So now
Yes, sir, that will be helpful.
I will now share the slides. So in the last class, I did not solve this problem, saying that it would take some time. So I would like to take it up in today's class. So let us read the problem. Here there is a hollow cylinder with 30 millimeters inner radius and 50 millimeters outer radius. That means this has got a 2 centimeter thickness, this hollow cylinder. And K is 15 watt per meter Kelvin. The thermal conductivity of the material of the cylinder is 15 watt per meter Kelvin, is heated on the inner surface at a rate of 10 power 5 watt per square meters, and dissipates heat by convection from the outer surface to a fluid at 100 degrees Celsius with heat transfer coefficient of 400 watt per meter square Kelvin. Find the temperatures at the inside and outside surfaces of the cylinder. Okay, so this is the problem about a cylindrical shell or a hollow cylinder where there is a certain heating taking place at the inside and there is some heat transfer on the outside. Now you see there is a lot of information given. If I count what the number of numerical data given, you have the inner radius, outer radius, thermal conductivity, heat flux, outer fluid temperature, heat transfer coefficient. So 6 numerical information is available in this particular problem. It's always better to draw a schematic diagram so that these things will be easy to understand for you. So I will do that. So first, as given in the problem, this is a cylindrical shell. So I'll draw a cylindrical shell here. Fortunately, I'm not so good at using this digital pen, or I'll just do it once again. Repeat it. So this is the cylindrical shell, and it is 30 millimeter. Millimeter, and at the inside you are given the heat flux is given here. A is in watt per meter Kelvin, and also inside heat flux is given as 10 power 5. Watt per meter. And outside there is a fluid at 100 degrees Celsius. So here we have a fluid flowing, let us say T infinity is 100 degrees Celsius. Transfer is 400. The quotient is 400. So we are asked to find out what is temperature at the inside and outside surfaces of the cylinder. So and temperature here. Ti is how much? To is how much? Now see here, the outside temperature can be different from the fluid that is flowing. So if the fluid temperature is 100 degrees Celsius, this doesn't have to be 100. In some cases it can be, but it doesn't have to be 100 degrees Celsius. It can be different from 100 degrees Celsius. So that is something we need to find out. And also see here you have Q prime, which is 10 power 5 watt per meter square, which is the heat flux condition given. So at the inside wall we have some heat flux condition. Usually this kind of a constant heat flux implies that there is electrical heating taking place on the inside. So probably there are electrical coils mounted on the inner wall, which are constantly supplying a heat at a rate of a heat flux 10 power 5 watt per meter square. So that is the practical significance of this problem, or the practical implication of this problem. Okay, so we need to find out what is the value of Ti and T out. For that, how to solve this problem? Now this is something related to a cylindrical shell and conduction inside a cylindrical shell. Okay, now let us work out a plan for this. Knowing the conductivity of this particular material, we are given K is 15 watt per meter Kelvin. Knowing the conductivity, can we calculate the resistance of the material, thermal resistance of the material? The value of R, can we calculate? We know the conductivity, we know the inner radius, we know the outer radius. So Ri is known, Ro is known, K is known. Can we calculate the thermal conductivity of this cylindrical wall? I'm talking about this wall. This wall It's not plain wall, it's a cylindrical wall. Can we calculate the resistance of it?
Yes, sir.
What's the formula which we can use? Okay, the formula is somewhere in the data book. We'll come to that. So we can calculate the thermal resistance of this material. So when we can calculate the thermal resistance of this material, and knowing this inside and outside temperatures, can we write an equation for the heat transferred across the wall, heat conducted across the wall? There is a temperature difference. Temperature difference divided by the resistance will give you the heat transferred across the wall. Okay. Now this heat transferred across the wall is also same as the heat carried away by this fluid, right? Okay. So if we can equate this heat transferred across the wall to the heat carried away, we will get some equations. So in that way, we can generate some equations. Remember, to solve this problem, we have two unknowns, Ti and Tout. So we should at least have two equations. We should be able to generate two equations involving Ti and Tout. We'll see what else we have. See, we did not talk about this 10 power 5 watt per meter square here. This is the heat flux at the center, inner surface. The cylinder is heated on the inner surface at a rate of 10 power 5 watt per meter square. So at the inside, this heat flux is applied. So if this is the heat flux is heat per unit area. So if we multiply this heat flux with the inside area, we will get what is the amount of heat transfer. So this amount of heat transferred, if you calculate, that can be used to generate one more equation. So we will know the amount of heat transferred on the inside. That is same as the heat conducted across the wall, and that is same as the heat convected from the outside wall to the fluid medium. So in this way, if you try to generate some equations, we will be able to find out the values of Ti and To. So this is how you need to utilize the information given. And if the number of unknowns are same as the number of equations, then it will be easy to solve. Okay. Now let us try to write down the equations. Firstly, in data book, page 53, you will see thermal resistance. Of cylindrical wall. R is given as 1 by 2 pi k L log of R2 by R1. R2 is R outer divided by R inner. O stands for out, I stands for in. Now this is the resistance. Now in the problem, do we have the length of the cylinder? Length of the cylindrical shell? Is it given in the problem? No. Let us assume that let length be 1 meter. That means all the calculations that we do will be representative of a unit length cylinder. Okay, so using this we can now proceed. We know the value of K, L we have taken as 1, R outer and R inner are also known to us. Okay, so now I'll try to calculate the resistance. Resistance is 1 by 2 pi multiplied by K is 15 multiplied by length is 1 multiplied by log of R outer is 50 and R inner is 30 millimeters. Now I have not converted this 50 millimeter and 30 millimeter to meters, because you can see I have taken a ratio here. So whether if you convert it, that 10 power minus 3 in the numerator and 10 power minus 3 in the denominator will cancel off, and therefore we will still get the same result. So this will be the thermal resistance. So calculate the thermal resistance. What's the value?
Sir, it's coming around 5.42.
42 multiplied by 10 power minus 3. What's the unit of thermal resistance?
Sir, ohm.
No, it's not electrical resistance, it is thermal resistance. See, electrical resistance, see, we are only deriving an analogy, using an analogy between electrical conductivity and thermal conductivity. So you will find the unit here in page number 52. Again, it is Kelvin per watt. So this is the resistance. Okay, now at the inside, at the inner surface, Q is equal to heat flux multiplied by area. We have at this inner surface, we have the heat flux. That if we multiply with area, we will get the heat transferred at the inner surface. So this will be 10 power 5 multiplied by area of the inside. Area of the inside. What is the formula for area of the inside? It is a cylindrical circumferential area. So with the inner radius. So this will be 2 pi r inner multiplied by L. So this is 10 power 5 multiplied by 2 pi into inner radius is 30 millimeters. Convert that to meters. Multiplied by length is 1. So how much is this? How did you understand why I have taken that? 2 pi r L is the area. 2 pi r is the circumference, that's the length, multiplied by the length of the cylinder will give you the area. So that means when you cut open this cylinder and spread it out, the inner surface will look like a triangle where the length is L and width is 2 pi r I. So this basically will be, if you cut it open and spread it out, this will look like this. This is L and this will be 2 pi r I. That's why 2 pi r L has been taken. So this will be 18,840 watts. Okay, so this is the amount of heat that is being transferred at the inner surface. Now, under steady state conditions, the heat transfer from inside to outside will be the same. There is no accumulation. So, the heat transferred on the inner surface should be same as the heat transferred at the outer surface. So, we know this heat transferred at the inner surface now, which turns out to be 18,840 watts. This should be same as the heat transferred from this one. Okay, now let us bring in this conductive resistance of the wall. We have evaluated that to be 5.42 multiplied by 10 power minus 3. So using this conductive resistance, I can express the heat transferred across this wall using the conductive resistance, the inner temperature and outer temperature. So heat conducted across the wall is equal to del T divided by R. Now, del T is T inner minus T outer divided by R, 0.42 into 10 power minus 3. Now, what is the value of heat conducted across the wall? heat conducted across the wall. We have calculated that. See, this is the heat flux applied on the inner wall. So the heat transferring from the inner wall into this material will be same as the heat conducted across the wall. Will be same as the heat convected from the outer wall to the medium. So see, the same thing, it will flow from one side to the other side. See, it's like a network of pipes. You may have three different pipes connected, three different diameter pipes connected. The flow rate in each pipe will be the same. Likewise, the amount of heat transferred in each pipe will be same. Just like the current along passing through each resistance connected in series will be the same. So the amount of heat transferred is 18,840. Is 18,840 watts. Or we can write this as a Ti minus To is equal to 5.42 multiplied by 10 power minus 3 multiplied by 18,840. So this will be 102.1. So I can write it here, Ti minus T out is equal to 102.1. So this is one equation we got in terms of Ti and T out. We need another equation. So for another equation, what we do is we write the heat transfer equation for the convection part. From the outside wall to the medium, there is convection taking place. So I will write the convection heat transfer equation. Heat transferred from outer wall to the fluid is by convection. So Q outer wall is equal to HA delta T. What is the value of H? H is given as 400 multiplied by what is the area out on the outer wall? Outer wall area. Again, this same figure applies, but the length is same, but this width will be, instead of 2 pi Ri, it will be 2 pi Ro. So the area will be 2 pi R outer multiplied by length. So this will be the area multiplied by delta T is the difference between this surface temperature and the fluid temperature, TO minus 100. So this will be 400 multiplied by 2 pi multiplied by R outer is 50. 50 by 1000, we'll convert it to meters, multiplied by length is 1 meter, multiplied by T naught minus 100. Now, heat transferred from the outer wall, how much is that? This again is 18,840. Okay, so now we'll evaluate the term in the brackets. So 18,840 is equal to 125.6 multiplied by T naught minus 100. Or T naught minus 100 will be therefore T naught is equal to 250. Okay. Now this is the second equation we have in terms of Ti and T naught. Anyway, Ti is not present in this equation, but this becomes our second equation. So we have T naught is 250. You substitute that here. So Ti is equal to T naught plus 102.1. 250 plus 102.1. So 352.1 degrees Celsius. Okay, so this is the inner temperature. So finally, the answer is inner temperature is 352.1 degrees Celsius, and the outer temperature is 250 degrees Celsius. Okay. So what you need to understand from this problem is, firstly, under steady state conditions, heat transfer across any number of resistance will be the same. I'm not saying heat flux will be the same. Heat flux will be different, because in radial systems, in curved systems, the inner radius and outer radius are different. Therefore, the area will be different. Therefore, heat flux will be different, but heat transfer will be the same. So that we have used here. So in the inner wall, we are given certain heat flux. Using that heat flux and the inner radius, we could calculate the heat transferred at the inner wall. Now, under steady state conditions, heat transferred on the inner wall should be the same as the heat transferred across the wall. It should be the same as the heat convected from the outer wall. So using these concepts, we have developed some equations. We know that there are two unknowns in this problem, therefore we need two equations. So we came up with the heat balance equations and arrived finally at equations in terms of temperature, Ti and To, and two equations, two unknowns. We could solve it to find the inner temperature and outer temperature. Is it clear? Do you have any questions to this point?
Sir, is Ti the temperature along the inner radius?
Yes. Inner
Okay,
surface,
sir.
Ti, and T out is the outer wall temperature. So the equations for this in the data book are given in page number 53. Okay, so there the schematic is very clearly given. The inner and outer temperatures are Ti and To, and the inner and outer radii are R1 and R2. Okay. Now we have taken L as 1. It doesn't matter whether the L length is some other value, because somewhere in the process the length get cancelled out, and therefore we don't really need the length. So that's about the problem number 3. This problem number 4 we have solved yesterday, so we'll move on to the next problem. Okay. Now this appears to be a slightly lengthy problem, but it's actually a simple problem. Let us read the problem. A house has a composite wall of wood on the outside, fiberglass insulation, and a plaster board inside. So there are 3 layers: 10 millimeters thick wood, 100 millimeter thick fiberglass insulation, 20 millimeter thick plaster board, and the conductivities also are given. The inside and outside temperatures are 20 and minus 15 degrees Celsius respectively. So the temperatures of the outer and inner extreme end temperatures are given. The total area is 350 meters square. The outer and inner convective heat transfer coefficients are 60 and 30 watt per meter square Kelvin respectively. Determine the total heat loss through the wall. If the wind were blowing violently and the outer heat transfer coefficient increases to 300 watt per meter square Kelvin, find the percentage rise in the heat loss. Then what is the controlling resistance? So that's the question. There are several questions asked, and also there are three layers of materials of composite wall. So fortunately, this is a plain wall. Therefore, the area will remain the same across all walls. So we are given the area as 350 square meters. So we will use that, and we'll try to evaluate that. So basically, this wall is a part of a room. A house is having a room in which the wall is made out of this composite materials. So we are asked to find out what will be the total heat loss to the wall, and If the heat transfer coefficient outside is changed, then what will be the thermal conductivity? No, sorry, what will be the increase in heat transfer? Okay, so again, to solve this problem, it's always better to have a schematic diagram. So we have 10 millimeters inside, 100 millimeters in the middle, and 20 millimeters outside a thick wall. So first, let me draw that. So we have three walls. First one is 10 millimeters. Second one is 100 millimeters. Third one is 20 millimeters thick. Ten, 100, 20 millimeters. Now, what are all these materials? The outside wood. This is wood. In the middle, fiber. And plaster board inside. We're also given the, I mean, 10, 100 and 20. So outside is 10 millimeters. Change this. This is 20 and this is 10 millimeters. Wood is 10 millimeters. This is 10, fiberglass 100, and plastic 20. And again, thermal conductivity. This is K is 0.17. Here K is 0.03. Here K is 0.12. Now I'll say this side, and this side is the outside. Okay. Then the inside and outside temperatures are 20 and minus 15 degrees Celsius. 20 degrees Celsius, and this side is minus 15 degrees Celsius. The total area is 350 meters square. Area, each area is 350 meters square on each wall. So that is the heat is conducting across an area of 350 square meters. The outer and inner convective heat transfer coefficients are 60 and 30 respectively. So H is equal to 60, H is equal to 30 watt per meter square Kelvin. If the heat transfer is blowing violently and outer heat transfer increases to 300. So the second part of the problem, instead of 60 here, if it is 300, what will be the heat loss? That is the question. We will not bother about that as of now. Okay. Okay. Once I will have to cut the inside and outside temperatures are 20 and minus 15. That means the 20 and minus 15. These are not the temperatures of the walls. These are the temperatures of the medium. So at this medium, T infinity is 20, and here T infinity is 15. These values given here are not the wall temperatures. These are the medium temperatures. So that's why they are given as the inside and outside temperatures are 20 and minus 15 degrees Celsius. Okay, so this is the information given to us. We will have to find out what will be the total heat transfer. Okay, now this is a very straightforward problem from the composite walls concept. Now what you can see is, if you turn to page number 53 in data book, you will see that you have an exact situation where you have three three materials, and the convection conditions are given on the outside and inside on the either side. So using that, you will be able to calculate what is the total resistance, and once you have the total resistance, you can calculate what is the heat transfer. Okay, so all the formulas necessary are given in page number 53 of the data book. So now we'll write the general formula. We have to calculate the heat transfer for this composite slab. So delta T divided by R, overall temperature difference divided by R. What's the overall temperature difference? 20 on the inside and minus 15 on the outside. So 20 minus of minus 15 divided by R. You see here, this minus 15 has to be taken in the bracket because there is a minus before. So this becomes, numerator becomes 35. Now we have to find the value of R, the total resistance. Now you see here how many resistances can be offered. Firstly, the convective resistance here, conduction resistance here, conduction resistance here, conduction resistance here, and finally convection resistance here. So 5 resistances are there. So let me draw the diagram, resistance diagram here, or just below I will draw. So this is first one, 1, 2, 3, 4, 5. So this is T infinity 1. This is 20 degrees, and this is minus 15 degrees. So this node. In between, there are some nodes corresponding to the walls. Okay. Now, this resistance corresponds to convection, this corresponds to conduction, this corresponds to conduction, this corresponds to conduction, and this corresponds to convection. So, for convection, we know the resistance is 1 by HA, and conduction is L by KA, L by KA, L by KA, and 1 by HA. So we have to evaluate all these 5 resistances. So now I will write down the equation for the resistance. Total resistance is equal to 1 by HA plus L by KA. I'll say L1 by K1A. So this will be 1, 2, and 3. L1 by K1A, L2 by K2A plus L3 by K3A plus 1 by H out A. Similarly, this is H in A. So you can see in all of this A is common. So I will take out A. 1 by A. A is 350 given in the problem, multiplied by 1 by HI. HI is 30 plus L1 by K1. This is 20 millimeters. So 20 multiplied by 10 power minus 3 divided by K1 is 0.12 plus the second one is 100 millimeters. So 100 into 10 power minus 3 divided by 0.038 plus L3 is 10 millimeters. 10 multiplied by 10 power minus 3 divided by 0.17 plus the convection 1 by 60. Okay. Now I will go to the next page and I will break it up. 1 by 350 multiplied by, I will write each term separately because we will need that later on. So 1 divided by 30.033 plus second term is 0.167 0.059. Plus 0.016. Now this will give us the total resistance. So I'll evaluate that. 0.033 plus 1 by 350 multiplied by 2.9057. This is 8.302 multiplied by 10 power minus 3 Kelvin per watt. So this is the total resistance. Now heat transferred is delta T overall divided by R. So delta T overall is T infinity 1 minus T infinity, or T infinity in minus T infinity out. T infinity inside minus T infinity outside divided by R. So this is 20 minus of minus 2. R is 8.302 multiplied by 10 power minus 2. Okay, so 4215.8 value, 0.8 watts, or this is 4.2 kilowatts. This is the heat transfer. Okay, so this is the first part of the problem. We could calculate the rate of heat transfer using the individual resistances. We have used this general equation that heat transfer is equal to overall temperature difference divided by the total resistance. So we computed the total resistance here along using the electrical network analogy. We computed it separately and then added all the resistances and substituted in this equation, so that we got the heat transferred as a 4.2 kilowatts. Now there is a second part of the question. Determine the total heat loss through the wall if the wind were blowing violently and outer heat transfer coefficient is 300 watt per meter square Kelvin. So if the outside H, so this H instead of 60, if it is 300, then what will be the value? So all you have to do for the next part of the problem is in place of 60 here, you substitute 300. So what happens? The resistance changes, and therefore, in fact, the resistance decreases, and therefore, the amount of heat transfer will increase. So we are asked to find out what is the percentage increase. So you calculate that percent. You can see the answer here. You will get it as a 0.7. Okay. Now there is a last question. What is the controlling resistance? What is the controlling resistance? Controlling resistance means just think about a situation where a work has to be done by 5 people. By 5 people, one after the other. A job has to be done by 5 different people, one after the other. One person is faster, other person, each one will have a different pace. So the time taken to complete that work is actually controlled by the slowest person, isn't it? Likewise, here also, we are asked to find what is the controlling resistance. So what is that resistance which has dominance over other things also, or other resistances? So in this case, you can see which one has got the highest resistance. You compare these values, 0.033, 0.167, 2.63, 0.059, 0.0167, which is the highest one. You can see that this is the highest one, 2.63. 2.63 corresponds to this value. So this corresponds to the fiberglass. That means the fiberglass is offering the maximum amount of resistance, and therefore that is the one which controls. Therefore, you can say, since resistance offered by fiberglass is maximum, it is the controlling resistance. That means, now you see here in this problem, this heat transfer coefficient on the outside, where it was changed to 300 from 60. From 60, it was changed to 300, and you can see that there is only 0.7% increase in the heat transfer coefficient. 0.7% is very, very less. That is because this outside heat transfer is not the limiting or the controlling resistance. Something else is. What is this? We found out from the magnitudes of the resistances that the fiberglass is the controlling one. That means to increase the heat transfer, what we have to do is we have to do something to this one, not just to increase, to decrease the heat transfer. So you'll have to alter this. You have to change either the thickness of this or the conductivity of this, so that the overall value changes considerably. If you alter the other things, then the overall heat transfer value will change only minutely, as we have seen just now. That is because they are not the controlling ones. Okay, so this is like let us think about India's overall well-being. There are poor people and there are rich people. The overall well-being of the country is let us say total sum of the well-being of the poor people as well as the rich people. Now, to improve the overall well-being of the country, we can either increase the well-being of the poor people or increase the well-being of the rich people. But what happens is, if you increase the well-being of the rich people, the overall country's improvement will be very minutely increasing, just like we have seen in this case. Therefore, if you have to improve the country's wellness, you should actually improve the wellness of the poor people. Then only the overall country will benefit. So this is another kind of an analogy which you can take from heat transfer. Okay, I hope you understood this. We'll go through the solution process once again, and things will be clear. It's quite simple. Okay, so if you have any questions, you can ask now. Otherwise, I will take the attendance. All right, give me your attendance. Rutunidhi,
Present, sir.
Vilash,
Present, sir.
and Cherian,
Present, sir.
Madhusudan,
Yes, sir.
Dilip, MV,
Present, sir.
Satsam,
Present, sir.
Maitreyan,
Sir, Pranazili present.
Maitreyan,
Present, sir.
Nivel,
Pioneer present, sir.
Ishant,
Present, sir.
Kalagan,
Present, sir.
Niranjan, Karan,
Present, sir. So, Vaibhav Karan present.
Sir, Niranjan present, sir.
Abhijit present, sir.
what about Niranjan?
Present, sir.
See, if you miss your call, then wait for the next time, okay? Because you'll stop the flow. Abhijit Menon,
Present, sir.
Pratik Krishna, Praveen,
Praveen present, sir.
Adil Sinju,
Adil present, sir.
Chaturvedi,
Present, sir.
Chintan,
Present, sir.
Hassan, Ayush Tripathi,
Present,
Sir, Hamza is present, sir. I'm sorry.
Ayush Tripathi,
Present, sir.
Harshavardhan,
Present, sir.
Hemant Kumar,
Present, sir.
Chandramouli Pratap Singh,
Present, sir.
Vania,
Present, sir.
I Rohit,
Present, sir.
P. Raman,
Present, sir.
Vishal AV,
Present, sir.
Deepesh,
Present, sir.
Venkat,
Yes, sir.
Sundar,
Present, sir.
Sundar Krishna,
Present, sir.
Present, sir.
Who is that? Sundar Krishna or Pranav?
Yes, sir. Sundar, sir.
Pranav, present, sir.
Jayanti,
Present, sir.
Iniket,
Present, sir.
Sri Narayanan,
Present, sir.
Vito,
Present, sir.
Ajit,
Ajit present, sir.
Harish Raghav,
Present, sir.
Sir, Rahul present, sir.
Firoz, Nihar,
Sir. Nihar, present, sir. Feroz, present, sir.
Vishnu Karthik,
Present, sir.
Shankar, Motishwar,
Motishwar, present, sir.
Jay Prakash,
Yes, sir.
Suja,
Present, sir.
Kumar,
Yes, sir.
Charan Sarvesh,
Present, sir. Gauri Shankar present, sir.
Charan Ajay, Reynold Simon,
Present, sir.
Vamsi Krishna,
Present, sir.
Venkatesh,
Present, sir.
Anakshaya,
Present, sir.
Kiran Dev,
Yes, sir.
Arun,
Present, sir.
Al Rao,
Present, sir.
Vignesh Kumar, Vignesh Krishna, Vedant Madhur,
Present, sir.
Anand,
Present, sir.
Shivani,
Present, sir.
Priya Vasan,
Present, sir.
Salai Priyan,
Present, sir. Sir, Kalai, present.
Shankar Narayanan,
Present, sir.
Anish present, sir.
Santosh Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Ash Kumar,
Present, sir.
Karthik Prasanna, Sai Kaustab,
Present, sir.
Varun Ahalyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
LC Femina,
Present, sir.
Effort Gionel,
Present, sir.
Mal Manoj,
Present, sir.
all the absentees. Pratik Krishna, Hemant Kumar,
Hemant, present, sir.
Gauri Shankar,
Present, sir.
Sharan Ajay, Vignesh Krishna, Karthik Prasanna,
Present, sir.
all right. So you go through the solutions, and if you have any questions, you ask me. And also, these are all very standard problems. Most of the problems or similar problems will be solved in all standard heat transfer textbooks. So try to go through the examples, try to work out the exercise problems on your own, then you will have some confidence in tackling these problems. Okay? So we'll meet again on Monday.
Thank you, sir.
Thank you, sir.
Thank you.